Hey folks, this is Doug, and we are going to start to introduce the organometallic reactions. This is actually a huge topic. It should be a whole course, but we've just got one chapter finally. Organometallics are becoming chapters in organic chemistry books, which they absolutely should be. You should start getting an introduction to this. So I'm just going to tell you, give you some basic definitions. Why are these important? Where maybe have you seen them being used before? And then talk about what reactions we're going to focus on for this section. So first off, right, organometallic is exactly what it sounds like. We're talking about compounds or processes that involve having some organic piece attached to a metal, right? And we've already talked about some organometallic reagents in the past, right? We talked about these organolithiums and these organomagnesiums, right? We had things like CH3Li, or we had these organomagnesiums like, I'll put CH3MgBr, right? We call these the Grignard reagents. And we saw them in reactions, right? Like, for example, if I had a carbonyl and I added step 1 PHMgBr and step 2 little acid workup, we saw that we could make new carbon-carbon bonds. So this is really important stuff. And we're going to compare and contrast these to some of the palladium-catalyzed cross-couplings later. But in all of these, right, the idea here is that you have a metal carbon bond, right? So we've got this metal carbon bond. Here we've got your lithium, which is attached to the carbon. That's a carbon-metal bond. And your magnesium, which is attached to the carbon in the CH3. That's your metal carbon bond, right? So those are our organometallic things. One example that we didn't really get into, we've certainly talked about it, but we never really mentioned that during catalytic hydrogenation, right? So if you had something like an alkene and you added like H2 and palladium or nickel or something like that, that reaction is actually technically an organometallic reaction. Organometallic reaction. And that's because, and you may remember this from when we were talking about this, right, that the idea here is that if it's a heterogeneous, right, so you don't have a mixing of things versus homogeneous. So if you have a heterogeneous catalyst, right, and this is palladium, so your surface of your palladium, the idea is that at some point your alkene is going to be attached to your palladium at somewhere. So you have this, again, this metal carbon bond. Here's your organometallic bond, your metal carbon bond. So we've seen examples like this before, but these are just the tip of the iceberg. Catalytic hydrogenations are all over the place, but we need to start talking about the more sophisticated ones in a second. But like I was saying, these are really important reactions. So last number I saw was that there's an estimation that about 70% of all the reactions in pharmaceutical and fine chemical production are organometallic reactions, right? Which is a huge, huge number. And that's why I'm so glad that these reactions are finally showing up in organic chemistry textbooks, because we're talking about making organic molecules, and so often we use organometallic reactions. So like here's an example of making ibuprofen, which had an older process, but this is a newish process where it's just 4 steps. If you take a look at the first step, that's just a Friedel-Crafts acylation, right? You were using acetic anhydride, the AC2O, to put on this group. But then in the next step, you have a catalytic hydrogenation, which is organometallic. Right, this is an organometallic reaction here. We just reduced our carbonyl, right? We added that H and we added this H. So there's, in the synthesis of ibuprofen, there's an organometallic reaction. And there's not one, but there's actually 2, because then here, right, see, we've got palladium. This is actually also an organometallic reaction. So of the 3 reactions in your synthesis of ibuprofen, 2 out of the 3 are organometallic reactions. And in this case, you're actually inserting a CO in between where that alcohol was and that secondary carbon was. So that's just an example, right? It made the old process it's much shorter than the old process. It has a higher atom economy in the process. You use a lot more of the waste, so the E factor is much, much, much better for this reaction than the old reaction. And so we're going to see lots of examples of how organometallic reactions actually make our lives a lot easier, a lot greener, and save us a lot of time. You may have also heard, right, here's another example. Here we are starting with ethylene, or also named ethene, right? So the IUPAC name would just be ethane, but it's also known as ethylene. And then here on the right-hand side, right, we're just polymerizing it to make polyethylene. Polyethylene, or PE. Right? Super, super, super common plastic. And say what you will about plastics, but they have changed the way that we have lived. And this is one of the reactions that really allowed us to make huge amounts of it. And so this is called the Ziegler-Natta polymerization. They actually won a Nobel a while ago for this reaction, for making these, finding a good catalyst to make these polymers efficiently and predictably. But here's our catalyst here, right? This is our catalyst. This is one of the catalysts. There's many that the Ziegler-Natta catalysts out there, but this is one of them. So this is our catalyst. And you can see that I've got a zirconium, and it's got all these bonds to carbons, right? It's only got carbon ligands on it. It's only got carbon groups on it. And the term ligand, right, I have down here, the ligand is just any molecule or ion, could be like chloride or something like that, any molecule or ion attached to a metal to form a coordination complex. So all of these things would be considered ligands, right? All of those are ligands. And what you'll see is that we'll often abbreviate ligands as just L, just an L. So I could have written I could have also written this as zirconium. Let me make that ZR a little bit better. Could have written this just as zirconium with L4, because it's got 4 ligands on it, right? It's got 2 cyclopentadienyl groups on it, a methyl group, and an alkene on it. So we'll see lots of L's as just abbreviations for ligands. And if you hear the term ligand, it's just anything that's really bound to a metal in a coordination complex. Right, so here are 2 mechanisms for hydrogenation and hydroformylation. The mechanisms for these reactions, these catalytic cycles, are very, very different than what we're used to seeing. Since this is an organic chemistry class and this is not an organometallic class, I'm not going to ask that you know these catalytic steps or these elementary reactions. So if you're looking in your book and you see stuff about oxidative addition or alpha elimination or alpha migratory insertion or any of that sort of stuff, you can just skip all that. Don't worry about it. I'm not going to ask you any mechanisms. I want you to be able to identify what type of organometallic reaction it is and predict products and be able to use them in a synthesis. While I have this up here, though, I did want to point out, like I was saying on the previous slide, that we will see like just L, right? Here's just L's written out, and that's not some element. These are just ligands, some just generic ligand on a metal, in this case, rhodium. So just you'll see these abbreviations out there. Don't worry about it. They can be a lot of different things. They're really important, it turns out, but they can be lots of different things, not important to us for organic chemistry. Now, like I was saying, they're super important. I did mention earlier that Ziegler and Natta won a Nobel Prize in chemistry for their polymerization catalysts. In 2010, which is the most recent one where folks have won for organometallic reactions, Heck, Negishi, and Suzuki all shared the Nobel Prize in 2010 for their work on palladium-catalyzed cross-couplings in organic synthesis, right? So this is something that we're going to talk about in the upcoming videos. And they have their own reactions. There is something called the Heck reaction. There is the Negishi reaction. There's the Suzuki reaction. They all have their own named reactions. And there's lots of other named reactions. There's also things like the Stille. There's also Stille, Sonogashira, Hiyama. There's all kinds of named organometallic reactions, and that's just because they differ in what your coupling partner is, what your metal is. We are going to focus on just a few of these. So we're definitely going to talk about Suzuki because that's a real big one, and we're going to talk about Sonogashira because it's also a pretty big one, especially at the U of O, which is where I did my grad work. There's a group there that did a ton of them, so I'll show you a little bit of their work. But it's a really, really big deal, right? So this is the second Nobel Prize that I'm showing you just in this slide that have gone to people doing organometallic chemistry. Again, the big reactions that we're going to talk about, we're just going to focus on 3. We're going to focus on the Suzuki reaction, the Sonogashira reaction. Let me do that in a different color, Sonogashira, and we're going to do the grubs. We're going to talk about olefin or alkene metathesis. Grubbs also won a Nobel, by the way, and I'll mention that again in another video. He also won a Nobel Prize in chemistry in, I think, 2005 or something for this work. So there's 3 Nobels just for organometallic reactions, just for discovering new ways to make molecules, right? So it's a big deal. It's a really, really big deal. I'll show you this slide again in all of the future videos here, but the Suzuki reaction is where you take a molecule, like we have this with this leaving group here. Lg stands for leaving group. And I'll talk about what those are in future videos. But the Suzuki reaction is where you take a sp2 hybridized something with a leaving group and you add a boron containing piece and you couple them together. That'd be this top route. That'd be this route. If we're talking about the Sonogashira, that always involves an alkene. And it's a way to make, or sorry, not alkenes, alkynes. It's a way to make alkynes. It's a way to add a group where that terminal hydrogen was. You can add a different group there. And I'll point this out again, but what's important about this is that it's not a group that you can attack with an SN2 reaction, right? So this is going to allow us to make more alkynes than we had with just taking off that terminal alkyne H and doing an SN2 reaction like we learned in the past. This is going to be more useful. And then we'll also talk about the olefin metathesis. We'll look at Grubbs catalyst just real generically and talk about how you can take a alkene and you can basically replace the halves. You can make the halves switch. It's called a metathesis. So you can get 2 of the A sides connecting and then 2 of the B sides connecting. You can actually make the alkene sort of swap partners. So you break that carbon-carbon bond and reattach it with other things. And we'll look at those. So we're going to look at Suzuki, Sonogashira, and olefin metathesis. That's what we're going to be taking a look at. So I hope that gives you a little better idea of kind of what organometallics are, a little bit of definitions. It's a big deal. And then we'll take a much closer look at the Suzuki, Sonogashira, and Grubbs. All right, happy studying.